All right. I will begin with a word of prayer. So, here we go. Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right. So I'll begin here with let me get this ugliness out of the way. There. So definition, and I'm going to write this up here. For a linear transformation on an inner product space V, T so inner product space so it's got some inner product, right? We say number one. So for the field being the real numbers, all right, T is orthogonal transformation if inner product of Tx with Ty is equal to inner product of x and y for all x and y in the vector space. So this is what it takes to be an orthogonal transformation, is it doesn't change the inner product between two vectors. The inner product is maintained. This is an orthogonal transformation. Point number two, for the field being the complex, all right, then T is a unitary transformation. Unitary transformation. If, again, same condition, the inner product of T of x with T of y is the inner product of x and y. All right? So this is what it takes to be a unitary transformation. This is what it takes to be an orthogonal transformation. What can we say about orthogonal transformations? Well, they maintain the angle between points. Do you guys remember how we defined the angle between 2 points, between two vectors? How was it defined? It was defined by the ratio of what? Comment. If we look at the norm of x, right? That is equal to the square root of what? X and x, right? But if we're looking at an orthogonal transformation or a unitary transformation, we could just as well write that what? T of x, right? Which would be what? The length of T of x, right? So if we preserve the inner product under the transformation, that means we preserve the length of vectors. So one thing an orthogonal transformation or a unitary transformation will do is it will maintain the length of vectors. All right? Another thing, of course, how do we define, let's keep it real for a second here. Just to be specific here, take the field to be the reals. How is the angle defined? Remember? We said cosine of, so the angle between, say, vectors x and y, both non-zero, right? We said that cosine of theta was, by definition, the inner product of x and y divided by the length of x times the length of y, right? So what's that equal to? For an orthogonal, we can just as well write that the inner product of T of x, T of y, divided by the length of T of x, the length of T of y. So that says that the angle between x and y, right, is equal to the angle between t of x and t of y because they both give the same cosine. Does that make sense? So the angle between vectors is also preserved by an orthogonal transformation. So what does that mean? If your transformation maintains the angle between vectors and if it also maintains the length of vectors, what does that say about the transformation in terms of geometry? What's it doing? I heard it's rotating, it's just rescaling. I would agree with one of those things possibly, but not necessarily. I mean, it could be rotating, but it could also be reflecting. Like reflections are not rotations, but they also maintain the angle between vectors and the length of vectors. All right. But yeah, I mean, it's preserving the shape of things is what's going on, right? If you thought about taking a square, you know, and passing it through an orthogonal transformation, the output should again be a square. You know, if you take a equilateral triangle and you pass it through an orthogonal transformation, your result's going to be an equilateral triangle. It's going to maintain the length and the, you know, relative positions of vectors in space. Yeah. All right, so that's, you know, the basic idea. I have more to say in the notes, but I'll just kind of leave it at that here. You can also talk about definition ONR is equal to A in Rn by n such that A transpose A is equal to the identity. This is for orthogonal. So this is the set of orthogonal n by n matrices, aka the orthogonal group of n by n real matrices. The reason that it's called the orthogonal group of n by n real matrices is that it's a group formed by orthogonal matrices. So it's not that surprising. Now, you guys don't know what a group is, right? Maybe you do, maybe you don't, I don't know. But a group is a set that has an operation which closes back on the set again, meaning it's a binary operation. There's an identity for the operation. Every element has an inverse, and the operation's associative. This is a group. Now, I don't expect you to know that in here, but the next course we'll spend, not will, but Dr. Sprano and you guys, will spend the better part of the semester investigating the definition of a group and what it means, all right? This is an example of a group, though. Now, that's orthogonal n by n matrices. There's also, you could talk about SON R. This would be A in ON such that the determinant of A is equal to 1. In other words, to say that a matrix is an SON, which is the so-called special orthogonal group, the S is for special, is to say that it's an orthogonal matrix which has determinant 1. What are the possible values for the determinant of an orthogonal matrix? Let's look at that. What happens if we let A be an ON? What do you got? A transpose A is equal to the identity. So what happens if we take the determinant of that equation? What does that give us? So the determinant of the product is a product of the determinants, right? What's the determinant of the transpose of a matrix equal to? It's equal to the determinant of the matrix, right? So what you're looking at here is the determinant of a quantity squared. What's the determinant of the identity? It's just 1, right? So what's the determinant of an orthogonal matrix possibly equal to? Yeah, negative 1 or 1. Determinant of A is equal to plus or minus 1 are your choices. So half of ONR is what we call SON. That's the half of the orthogonal group, which is determinant 1 matrices. Those correspond to rotations. So it turns out determinant of A equals to 1 implies that A is an element of SONR. And when you look at that geometrically, it turns out that these are rotations. And when I say that they are rotations, what I mean is that if you look at the linear transformation on Rn, for which such a matrix is the matrix of, the standard matrix of, then that transformation is a rotation. Let me be more specific. So like you have T of x equals to AX. This transformation is a rotation, right? But you'd say A is a rotation matrix in this case. For example, n equals 2. That means A looks like cosine theta, minus, was it minus sine? I can't remember. Minus sine theta down here, I think. Sine theta, cosine theta. That, if you multiply by that matrix, it rotates your points. All right. In contrast, determinant A equal to minus 1, this gives us what's called a reflection. All right. An example of a reflection is, so for example, if I take T of x, y, z equal to, minus x, minus y, minus z, that would be minus 1, minus 1, minus 1 times x, y, z. That matrix, minus 1, minus 1, minus 1, the 3 by 3 matrix with minuses on the identity, minus 1s on the identity, that would be an example of a reflection matrix. The determinant of that is minus 1. And if you multiply that times its transpose, you get back to the identity. So that's in O3R. All right? This would be an example of a reflection. Okay, so that's what that is. I can say more. Maybe I should. If we were to calculate, let's say that A is equal to V1, V2, so forth. Suppose those are the columns of A, which is in ON, all right? Then what would A transpose look like? The transpose, right? V1 transpose, V2 transpose, Vn transpose, right? So we're assuming that A times A transpose is equal to what? Or I say, how'd I go? A transpose A, yeah. So what's that translate into here for the vectors that form the columns of the orthogonal matrix? Translates into stack of rows, V1 transpose, V2 transpose, Vn transpose, yeah, times V1, V2, Vn. So that's all equal to the identity matrix, right? So when we multiply that matrix out, what do we get? What is this matrix? Well, I'll tell you what it is. It's V1 transpose V1, right? V2 transpose V1, and so forth and so on, right? Can you guys tell me a better way to write those? What's V1 transpose V1 equal to? That's V1 dot V1, is it not? Right? So if you look at this, what you really have is, let me just go ahead and start writing it that way over here. V2 dot V1, no, the other way around. V1 dot V2, V2 dot V2, and so forth and so on. Vn dot v2, v1 dot vn, v2 dot vn, vn dot vn. And that's all equal to 1, 0, 0, 1. Let me write it in a slightly less weird way. So what we're looking at is the matrix with typical ijth entry vi dot vj, and that's equal to the identity matrix, which has typical entry Kronecker delta ij. So what this shows is that vi dot vj is equal to Kronecker delta ij, which proves that the columns of an orthogonal matrix are orthonormal. Question. What can we say about the matrix of an orthogonal transformation? If T goes from Rn to Rn is orthogonal transformation, then let's look at it. We have T of x, T of y, right? What is that equal to? Let's suppose that the standard matrix of T is A, all right? So AX, AY. But what is the inner product here in Rn? This is dot product, right? So we could rewrite that in what way? Like explicitly, what is the formula here? It's AX transpose times AY, right? So we know sock shoes, right? So this is X transpose A transpose AY, right? If this is a orthogonal transformation, what's this equal to? Yeah, this is supposed to be the inner product of x and y, right? If you allow me this short manga style calculation. So this is, like you just told me, X transpose Y, right? But not just for one pair of X and Y, but for all X and Y, right? So if you use your imagination, you can see that this says X transpose times the identity matrix times Y is equal to X transpose A transpose A times Y for all X and Y. And that says what? How about this? If we set X equal to EI and Y equals to EJ, we get EI transpose I times EJ is equal to EI transpose A transpose A EJ. Man, these markers are just dead. Do you guys remember, like the first couple weeks of class, one of the things we proved is if you take a matrix and you multiply on the left by the transpose and on the right by the standard matrix, that picks off the ijth component. So this gives us the ijth component. Is a long time ago, it still matters though. Iij, in other words, the ijth component of the identity matrix is equal to A transpose A, the ijth component of that. In other words, since this holds for all ij, because this was an arbitrary ei and ej, we've shown that I is equal to A transpose A. what I'm saying to you is an orthogonal transformation has a standard matrix, which is an orthogonal matrix. This is good, because otherwise the terminology would be very awkward, right? You understand that there was something to prove there, right? And hopefully this demystifies why we used that as the definition of ON, because that's the condition you need on a matrix to make it the standard matrix of an orthogonal transformation. Does that make sense? I hope it makes sense. Okay, so great. What about unitary transformations? What's the deal with that? So rather than giving you the definition for a unitary transformation at the start, let's derive it. What's the difference with, if I, instead of, can I, you guys, vote. Who wants me to erase this? Who wants me to erase that?
Erase
this. This? Erase all of it? All of it.
I've already written it all.
All right. Let's see here. Yeah. That does feel good. Thank you. All right. So let T be unitary. And to keep it relatively uncomplicated, I'm going to assume it's Cn, because otherwise I have to work with a basis, and I just don't want to at the moment. Be unitary transformation. What's that mean? And let's let T of, I'll use Z since it's complex, right? T of Z equals to AZ. There you go. Although traditionally a U is used for the matrix of a unitary transformation. But I'll stick with A so that you can see the commonality of the calculation here. All right, so then we have what? The inner product of Z and W is equal to the inner product of T of Z with T of W. Is there any marker in this? It's the worst marker day. Now, this is AZ, AW. But how did we define the inner product for Cn? It was not bilinear, it was sesquilinear, right? I mean, here's the formula. If I have Z with W, it was Z transpose W conjugate, I think, was one notation we could use for it. So it's the dot product of the Z vector with the complex conjugate of the W vector in some sense. So, okay, what's that look like here? AZ transpose times AW complex conjugate. I will find a marker that I like. Well, they're all like near death. You guys can't tell. It looks the same to you, but it feels entirely different to me. So this, so much better. I feel much better. It's like, I don't know. So there you go. Socks, shoes for the transpose, but the complex conjugate does not reverse order. It just maintains order, okay? That's the way it works. And so this is equal to Z transpose I W conjugate for all ZW in Cn. So what this implies, all right, is that A transpose times A conjugate is equal to the identity matrix. But this is not a very nice condition, right? Because there's no A. I mean, like, we'd like to find a condition for A which involves A, not A transpose and A conjugate all at once, right? So how can you take this expression and turn it into something that doesn't either doesn't have a transpose or doesn't have a conjugate. I guess that's impossible, but what happens if we take the complex conjugate of this equation? What happens? What's the complex conjugate of the identity matrix? Well, that's easy. I again, right? But over here, you have the complex conjugate of the transpose times the complex conjugate of the complex conjugate of A, right? Which otherwise is known as A star, A equal to I, where A star is by definition A transpose complex conjugate. So that's nice, because A star A, well, that's kind of an easier condition, right? It's just, at least A is appearing. And so there you go. U n is equal to A in Cn by n such that A star A is equal to the identity. These are the so-called unitary matrices. All right? What do you think SUN is? A and UN such that the determinant of A is equal to 1. Yeah. This again actually forms a group of matrices. All right. It's an infinite group. Unlike most of the groups you study in next semester, they're finite groups. You could count the number of elements in this. This is, you couldn't count. It goes on and on. Like rotations. How many rotations are there in the plane? How many? What angles are you allowed to rotate by? There's a continuum of angles, right? So the group of rotations is an infinite group. A lot of Dr. Sprano's focus next semester will be on finite groups, right? But infinite groups are also interesting because they appear as the groups corresponding to interesting geometric transformations. Okay, anyway. What condition is there on the determinant of a unitary matrix? Well, check it out. If we take the determinant of A star A, what do you got? Determinant of A complex conjugate transpose, right? Times the determinant of A equals to 1. But this gives us the determinant of A complex conjugate times the determinant of A equal to 1. This is a little bit sneaky, this step, but if you look at the formula for the determinant, it's built from a product of polynomials in the entries of A. And when you complex conjugate that, it's the same as, it's an identity that the complex conjugate of A, the complex conjugate of the determinant of A is the determinant of the complex conjugate of A. So you can pass the complex conjugate outside. The reason that's interesting is because then you have the modulus or absolute value of the determinant of A squared is equal to 1. That is to say that the length of the determinant of a unitary matrix is 1. That doesn't say it's equal to 1. What are the complex numbers with length 1? So if this is the real axis, if this is the imaginary axis, the determinant lies somewhere on the unit circle in the complex plane. It's somewhere on that circle. Here's 1. But it could just as well be up here, you know. You could have e to the pi I over 4. If you didn't, so generally speaking, guys, e to the I theta, Euler's formula says that's cosine of theta plus I sine theta. Fun fact. I don't know if that matters to you in the homework or not. There may be a problem. If you don't know about that and it comes up, come ask me about it. I'm happy to talk to you about it. All right. You know, you might wonder what's the relevance of special unitary matrices or unitary matrices. They're very interesting from the perspective of quantum mechanics. In quantum mechanics, you look at a wave function, which could be a vector in complex space. Like you could have a 2-component vector in complex space, a C2 vector. That might describe a physical system. The unitary transformations are the ones which preserve probability. Because the inner product, the complex inner product, describes the probability that you go from one state to another. So if I go like inner product of psi 1 with psi 2, that's the probability that you go from state 1 to state 2. And so if you do a unitary transformation, it preserves that probability. So they're probability preserving transformations. The special unitary groups are important for a variety of reasons. One of the reasons is that they appear in, uh-oh. Oh, that's right, it's not really plugged in. They appear in the symmetry groups of the standard model, so like SU2, SU3, and U1. These are all important symmetry groups for modern physics. They're something about the shape of physics is described by those in some sense, to be fuzzy about it. Any questions? So did you guys understand the video? Sorry about, I know you were alone. He apologized. He's like, I forgot. I'm like, oh, you did it yourself? Oh, wow. You took the initiative, and did somebody bring popcorn, or? No? Okay, well, good. All right, so let me go on here. So, I'm sorry, I'd write this stuff out on the board, but I asked to have the chapter printed, and the way the PDF works, sometimes they end up printing before because like the page numbering doesn't quite match up. And anyway, my printout ends exactly where I need to start lecturing here. And I probably would remember these things right, but there's a chance that it's just better if we look at it together like this. So, so what I'm about to describe to you in the next, so many minutes, 17 minutes, is the real spectral theorem. All right. So, essentially, well, the main point is this: I'll give you an overview, and then I'll read through it with you. So here's an overview. Number one, we'll define the adjoint for a linear transformation. So T star is a new linear transformation which is built from a given linear transformation T on an inner product space, all right? So my first order of business is to describe this new thing called the adjoint of T, all right? One of the major properties of this adjoint is it satisfies the following. If you have T of x with y, and you can do this, you can go, that's x times the adjoint of y. So, pretty cool, right? When you get into it, the matrix of the adjoint, with respect to an orthonormal basis, everything interesting in this section is for an orthonormal basis. All right. If beta is an orthonormal basis, what do you think the matrix of the adjoint of the transformation is going to be? If there's any notational justice, what does it have to be? So it's the matrix of T with respect to the beta basis star. Yeah, that is true. In the case of the field is equal to the reals, when we look at the adjoint of T, what is star reduced to when we have a real field? If the complex conjugate is stupid, if it does nothing, then the star, which is also known as the Hermitian adjoint, or just the adjoint of the matrix, is just transposition. So in the special case that you're working over the real field, this is just transposition. So for example, if you did have a linear transformation going from Rn to Rn, and you wanted to find the adjoint of that, all you do is take the matrix that you got for your transformation, Take the transpose of it, that defines the adjoint map. That's a special case of what we're doing, all right? But it's more than that in the complex case. So this is what we're going to do. We're going to define the adjoint, we're going to look at some of its properties, and then we're going to use it to classify a special kind of transformation called a normal transformation. And for those kinds of transformations, for those normal transformations, there's a real spectral theorem, which brings together the two concepts we've been looking at in this last story arc of the course, namely eigenvectors and orthogonality. A normal transformation allows for an orthonormal eigenbasis, which is really, really nice. All right. So let's look through it here. So I have to build some theory up for us to get to these results. Okay. So let me go through it. First of all, we talked about this before. If you want to, what is this? I'm saying that if you have an orthonormal basis, then you can find the components with respect to that basis by taking the inner product. We derived this the other day. This down here is saying the same for the ijth component of the matrix. You can calculate the ijth component of the matrix by taking the image under the transformation of Vj against Vi. This is like the next step. Remember, I spent, I don't know, 10 minutes, 20 minutes at the start of a class deriving this formula in terms of the dual basis and selecting the components for a transformation. This is very much part of that story. We'll circle back to that in maybe not next lecture, but the lecture after. I already proved this for you carefully, but I cheated. Instead of letting it be an abstract vector space, I used Rn or Cn to reduce clutter. But if you work it out for a basis, if you have an orthogonal transformation, it's got an orthogonal matrix with respect to that basis, but the basis has to be an orthonormal basis to make this true, and likewise for the unitary case. If you look at the proof, it's really just what I did sorting through a basis. My next thing is I define the adjoint. Now my definition is different than you'll find in a lot of theoretical linear algebra books. Theoretical linear algebra books like to use this condition right here. They use this condition right here to implicitly define the adjoint. They say T star is the transformation for which this happens for all x and y. I mean, that's true, and that is a definition, but it's also annoying because it doesn't give you a formula for T star, right? And if you ask a homework question like, calculate T star, calculate the adjoint of this map, and you're a linear algebra student, and you see that this is the definition for T star, it's very annoying because you can't just calculate it, right? In contrast, I have given you guys something very concrete over here as our definition. I say pick a basis, an orthonormal basis, define the adjoint like so. So what you do is you calculate T of the basis, and you inner product that with Y, and that's how you form the adjoint. That's a formula for the adjoint. Now, anytime in mathematics you define something in terms of a coordinate system, right, you're obligated to explain why there's no dependence on that coordinate system in this sense. Like if there was a dependence on the coordinate system, this wouldn't be a good definition, right? And so what I spend the next half page proving is that, in fact, guess what? It doesn't depend on the coordinate system. I sort through the formula in another coordinate system, and I show that it gives the same formula if I choose two different pairs of orthogonal bases, and I look at this, I can prove that that quantity is equal for both of those orthogonal bases. And they're arbitrary choices of bases, which shows you that my definition is independent of my choice of coordinate. All right. I will not test on this. Is my peace offering to you? Yes. I should test on the adjoint. What I'm saying is I wouldn't test you on the coordinate change thing I just mentioned, all right? That's a little bit much. Anyway, so theorem, this T star which I've just defined is a linear transformation, and guess what? It satisfies this condition that we want. All right, great. And the proof is right there. Here's the, let's go through this. This part of the proof is worth looking. I mean, the linearity is easy. The fact that when you move it to the other side, it gives you T on the other side, that's interesting. So let's start with this. then I have Vj with this is the definition of T star, right? Now, how do I move this out to that? What's that? Remember how it works? If you have a number multiplying the second component, it pulls out as the complex conjugate when you pull it out. That's the way the complex inner product works. But it's more than that because I have a summation, right? So the sum of the complex conjugates is the complex conjugate of the sum. So there's like a couple steps I'm really doing here, using the additivity of the complex conjugate and also the fact that we pull out conjugate of the constants from the second slot. But I get that. This is an orthonormal basis, so that's Kronecker delta ij. And so that kills the finite sum and leaves you with this. All right, so we've just proved that this is equal to that for all Vj. And if you can do that, then that you can, take a linear combination of this with arbitrary constants, and that gives you that x with t star y is equal to t of x with y. So if I can prove that for a basis, the identity follows, like I said, with a short calculation. But, all right, so again, A star is A conjugate transpose. This is the adjoint or Hermitian adjoint of a matrix. All right. So you guys already told me this on the basis of notation having to work, right? It must be, but there's the proof. Here are properties of the Hermitian adjoint. The adjoint of the sum is the sum of the adjoints. If you have a constant times t adjointed, you get the complex conjugate times the adjoint. It's got a sock shoes identity. That's because it's involving the transpose, right? So the transpose does the sock shoes thing, and the complex conjugate just stays put. The adjoint is back again. And finally, the identity is fixed under the adjoint. Now, that's all just sort of technical preliminaries. The reason this is interesting is because the adjoint has really neat properties with respect to the study of eigenvectors. So here's one. If T has eigenvector V with eigenvalue lambda, then the adjoint has eigenvector with eigenvalue lambda bar. Right? Now, I didn't say that V was necessarily the eigenvector. I just said it has an eigenvector, all right, at the moment. So here you go. If it has eigenvalue lambda, that means that there exists, well, like I said, V here, non-zero, such that this is equal to 0. What does that say? That says that this particular linear transformation has non-zero kernel, right, among other things. But anyway, so then I look at 0 is the inner product of 0 and x. I trade this 0 for the t minus lambda times the identity times v. Then notice that, now I stated the properties of the adjoint for the matrix, but all of those properties equally well apply for transformations, the adjoint of transformations. So what I'm trying to say is that what I'm trying to say is I had the adjoint of the identity matrix is the identity matrix. It's also true that the adjoint of the identity transformation is the identity transformation. That's what I need to use here. So there it is. But you notice I take this and I move it over to there. That's just something that's true for the adjoint. If you take a transformation, any transformation, move it over there, that puts an adjoint on it. And then by properties of the adjoint, this is t star minus the complex conjugate of lambda times the identity, x. All right? And so what we have is that v with this is equal to 0. What does that say about v? Well, it says that, let's see here. So I said, notice that this is in the range of that map. Does that make sense? I mean, that's the definition of range. And that means that v is perpendicular, right? I'm missing a range here, guys. There should be a range. It's the range of this perp, right? V is in the perp to the range of that mapping by this up here. So this is in the range, and that with something in that range is 0. That means that this is in the perp to the range. So if there's something in the perp, that means that the range is not all of V, right? Because if the range was all of V, it couldn't have something non-zero in its perp. So that shows that the t star minus this is not surjective, and hence it's not injective, which means that the kernel is non-zero, which is good news because the kernel of that map being non-zero is precisely what it takes for there to exist an eigenvector with eigenvalue lambda bar for the adjoint. And so there you go. Kind of sneaky, but there it is. Next up, there's Schur's theorem. Schur's theorem says that if we have a linear transformation over a finite dimensional vector space, and we have a characteristic polynomial for this, which is split, all right, so factors into linear factors, which is another way of saying that all of the eigenvalues are in your field for the transformation, all right? Then there exists an orthonormal basis for which the matrix is upper triangular, all right? So the proof is by induction on dimension, and I'm going to go on because we're a little bit short on time here today. But that brings us to the definition. V is an inner product space, and T a linear transformation. Then, like I said, T is normal. Is this interesting kind of transformation if T times T star is equal to T stars T? So if the transformation commutes with its adjoint, it's said to be a normal transformation. For an n by n matrix, it's normal if it commutes with its adjoint also, all right? So what are some examples of normal matrices? Well, symmetric or anti-symmetric matrices have A transpose A equal to plus or minus A squared, which of course is equal to A times A transpose. So like any symmetric or anti-symmetric matrix is normal, all right? Orthogonal matrices are also normal because of this calculation right here. Unitary matrices are normal, all right? So we have lots of interesting matrices we've already studied that are normal matrices. And here are the properties of normal matrices. So they preserve the length of vectors. If you subtract off a scalar multiple of identity, it maintains the normality of your transformation. This is stronger than the theorem I just shared with you because I'm not only saying that if you have lambda is an eigenvalue, then lambda bar is an eigenvalue for the adjoint of the transformation. I'm saying that that same vector x, that's the eigenvector for t, is the lambda bar eigenvector for the adjoint. That's stronger than the theorem I just proved for you here because it says that there's a connection between the eigenvector the eigenvector serves both as an eigenvector for t and its adjoint, just with different eigenvalues. And we also have that for distinct eigenvalues, the corresponding eigenvectors are orthogonal. Whoa, that's nice. That's really nice. Now, that leads us to the main event here, which is Theorem 9.6.13. Normal operators are orthonormally diagonalizable over the complex numbers. So if your transformation's over the complexes, that means that you have all your eigenvalues because the complex numbers are algebraically closed. And if you have a linear transformation on a finite dimensional complex inner product space V, then T is normal if and only if there exists an orthonormal eigenbasis for T. So, all right. We could look at elements of the proof next time perhaps, but let me just get to the point here. If you can check that your matrix is normal, right, that means that you can find not just an eigenbasis, you can find an orthonormal eigenbasis. That means it can be diagonalized. Not only can be diagonalized, it can be diagonalized in a nice way. When we look at this theorem just for the real case, the adjoint just drops to transpose, yeah? And so that brings us to this, one last definition here. We're almost done. If I have an inner product space and I have a linear transformation T, what's self-adjoint? Self-adjoint means that it's actually equal to its conjugate. Self-adjoint definitely implies normal, right? Because if T is equal to T star, then certainly T star is equal to T star T. So self-adjoint implies normal. And therefore, if you have, a self-adjoint transformation, well, it's even better. If you have self-adjoint then that means each eigenvalue of t is real. And if V is a real inner product space, then the characteristic polynomial for t splits. That's not obvious from the outset, but that's proved down here. So let me just, here's the take-home message from this. If you have a real symmetric matrix, it's self-adjoint. Therefore, its characteristic polynomial splits. That means it has all of its eigenvalues, and they're all real. So what this means is any symmetric matrix is diagonalizable. And not just that, it's diagonalizable in a really nice way. And that's what we're going to be looking at like next time. I'm going to actually show you how to apply this to solve specific problems. That's more what I test you on. I never have quite enough time in here to do justice to this theory. So, and I don't think you'll be too upset if I shortchange it, will you? No? Okay, so let's go on. I'll try to say a little bit more about the theory next time, but anyway, thanks.